Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I wanted to tell you about a very important theorem in the cohomology theory of coherent sheaves, and that is Serre duality. So I'll look in the special case of projective curves in this video, and in this particular case, Serre duality is often used to give effective vanishing theorems for H1. And as we saw before, since H1 gives the obstruction to exactness of the global sections functor, this is a very, very important and useful result. Okay, so let's see what our setup is. We're going to start with some smooth projective curve, X. It does work more generally. You don't need smooth, and the curve part is just for how I'll present it in this particular video here. We'll work over some algebraically closed field K here. We'll also need the canonical sheaf. Okay, so this is a critical part of the theory, omega X, also called the dualizing sheaf because it occurs in Serre duality. Okay, so one of the things that in this curve case that we know for this canonical sheaf is that we have this particular short exact sequence like this. Let's call it eta, from 0 to omega x to some extension to OX. So there's an extension of OX by omega x, and so in particular you get an element of this extension group x1 of OX into omega x. Okay, and if you look at that, of course, this is just h1 of omega x. Okay, so we have a canonical element of this h1 omega x. And the first part of the Serre duality theorem says the following. Okay, it's that this element eta is actually a basis for this h1 omega x. So this is just a one-dimensional vector space, and that means that we can find a isomorphism of h1 omega x with k, and I've denoted it with tr for trace. That's not an uncommon notation for that. Okay, so this is a big theorem, as is the main Serre duality theorem. I'm not going to prove that, but let's just go through a little example to see that it does indeed make sense. And this is the key place where it reduces to anyway, is to look at P1. So you can actually prove it by proving it in the case of P1. So let's see part of this, or let's see what happens in P1. So in P1, what's going on here? In this case, this omega x is just O minus 2, and we've calculated this in a previous video. And what is this extension here? What is this element? It's actually the Euler exact sequence, okay? So it's an extension of O by this omega x is O minus 2. And there is indeed a non-split extension here. Inside the middle here is O minus 1 to the direct sum 2. Okay, so if the coordinates of this P1 and x and y, there are the space of sections from O minus 2 to O minus 1. That's the same as the global sections of O1. So it's essentially it's spanned by x and y. That's the basis for those global sections. So you can have y minus x as the two maps into the two copies of O minus 1. And similarly, you can map these two copies of O minus 1 to O. So the homs from O minus 1 to O, also given by the global sections of O1. So here we'll use x and y. And of course, if you multiply these two matrices together, you get 0. And in fact, this sequence is exact. And this is called the Euler exact sequence. Okay, so in the case of P1, it's nice and simple like that. Something else that we've computed before is that if you take h1 of this omega x, that's O minus 2, okay, you do in fact get just a one-dimensional vector space, so it is equal to k. So this theorem certainly holds in the case of P1, and as I said, you can reduce the proof to this case. Okay, so what we're going to do is that we're going to use this to look at H1 of more general coherent sheaves. Okay, so suppose this script f is a coherent sheaf. Okay, what we're going to introduce is a certain dual pairing. Okay, so one of the things that we'll look at is the first cohomology of this f, H1xf. Sometimes I write the x in there, sometimes I don't. And we're going to pair it with what? We're going to pair it with hom of f into omega. Okay, so note this is a covariant functor of f, and this is a contravariant functor of f, and here omega makes its entrance here. Okay, so we've got an element of here, a pair. So C is inside this first cohomology group, and F is just going to be some homomorphism, some morphism of coherent sheaves from F to omega. And I want to pair these two elements together to get you an element, a scalar, so an element of K, and I'll denote it C, comma F. Okay, that's fairly typical. And how does this work? It's quite simple. So I'm going to define C, comma F as follows. I start with this C here, H1 of F. And since H1 is functorial, and you've got a homomorphism from F to omega X, okay, you can look at h1 of f as a homomorphism from h1 of f to h1 of omega x. It's just a linear map from here to here. So you can use this h1 of f, you apply it to here, and you get this h1f of c. That's an element inside this h1 omega x. And we have this trace map, which is an isomorphism from this h1 omega x to k. We apply this trace map to get a scalar, and that is what I'm going to call c comma f. Okay, so that's the definition of this bilinear pairing. Okay, so it's fairly natural, especially this bit here. Okay, and then you have to use this trace isomorphism. So there exists one, and you pick that one, you fixed it, and then you have this dual pairing. Okay, so what can you do with this dual pairing? Okay, so you have a bilinear map, and whenever you have a bilinear map, that gives you a map from one of those factors to the vector space dual of the other. And let's just have a look and see how that works. And this is what's going to give us Serre's duality theorem. Okay, so we have the following natural isomorphism. Okay, we have h1x of f. I'm going to map this to the vector space dual of hom from f to omega. Okay, so that's a star here denotes vector space dual. So from here to the vector space dual of that. And how do I do that? Well, I pick an element c inside here. There's my c. Okay, and what I can do is I can fix that c and look at this pairing, and I look at the function which just pairs things inside here with this c. Okay, so you can put elements of hom from f to omega like these f's in here. Okay, and as a function of the second variable here, this is a linear function, right? It's a bilinear pairing. So that gets you a homomorphism or a linear map from this hom space to the k. Okay, that's where it ends up. And it turns out this is an isomorphism. Okay, that's the Serre duality theorem, and in fact it's a natural isomorphism. So what do I mean by natural isomorphism? Okay, here you have a functor on coherent sheaves, h1. Here you also have a functor on coherent sheaves, hom of this f. Okay, the f can vary into omega, and then you take the vector space dual of that. This is a covariant functor. The hom is a contravariant functor, but when you take the vector space dual, it becomes a covariant functor. Okay, so these are both covariant functors, and as covariant functors on the category of coherent sheaves on this x, these are naturally isomorphic. Okay, so that's what the naturality means in this case. So that's a really, really nice result. Okay, so this is a big theorem. I'm not going to prove it, but let's just see that it makes sense by checking what happens on x equals p1. So x equals p1, so remember we have Grothendieck splitting theorem, so I guess the most interesting case is to look at the invertible sheaves O minus n, where this has a non-trivial h1, so where n is greater than or equal to 2. And we've calculated that this is just an n minus 1 dimensional vector space over k. Okay, that's what happens there. So if we have f equals this O minus n, we get this k to the n minus 1. Okay, what about on the other side? This should be isomorphic, so let's work out what this other side is. So we're looking at hom of O minus n into the omega, which is O minus 2, and we want to look at the vector space dual of that. Okay, so remember we're hopping from here to here. And remember tensoring by an invertible sheaf is a category equivalent, so we can tensor these two by some invertible sheaf that cancels this one. So that's O of n to make that an O. And you tensor this by O of n to make this O of n minus 2. And you're looking at homs of O into O n minus 2 and the vector space dual of that hom space. Of course, homs from O into this is just a global section, so that's H0 of O n minus 2 star. Now, of course, what's the global sections of O n minus 2? That just is an n minus 1 dimensional vector space, and taking the dual is still an n minus 1 dimensional vector space, so that's k to the n minus 1. So in this case here, at least these two are indeed isomorphic for f equals these invertible sheaves, and you can check that this is true also of the other invertible sheaves, so you get this result also in the case of direct sums of these. So they're all the torsion-free ones. And I guess the only other thing that you need to check for P1 is all the torsion elements. And if you look at the torsion case, we've shown that in this case, this H1XF, the first cohomology vanishes. And of course, if this is torsion, you can't map to this torsion-free, okay? The only maps from a torsion to a torsion-free are the zero maps. So this is 0 as well. So in that case, they also can be seen to be isomorphic. Okay, so the main reason why we use this, at least for curves, one of the main reasons is to make sure we have an effective cohomology vanishing theorem. Okay, and I want to show you how this works. Firstly, a little definition, which is very important in this theory, and that's the geometric genus of a smooth curve, a projective curve X. Okay, this is just the dimension of the global sections of omega X, which is also the dimension of the first cohomology of O. Okay, so why are these two equal? So the answer, Serre duality. Okay, so let's just put in O inside here. Okay, if you put O inside here, you have HOMS of O into omega. That's just H0 of omega. H0 of omega, so its dimension is the same as the dual vector space. So that's little H0 omega. And that's the same as the dimension of this space here, and that's little h1 of, we put f equals over there. So that's why they're the same. And this is commonly denoted G for genus, sometimes with either bracket X or subscript X if you need that. So what's the effective vanishing theorem that we want to use here? That's very common. So suppose D now is some divisor on X. Okay. So let's just have a look and see what Serre duality means in this case. That's fairly easy. It's going to mean the following. H1 of X OD is going to be the dual of an H0, and the dual of which H0 here is omega X minus D. So omega X minus D is the tensor product of these two invertible sheaves, omega X minus D. Okay. So that's just a fairly simple restatement that I'll show later of Serre duality in this particular case. But the important part is if the degree of D is bigger than degree of omega X, then this H1 will vanish. Okay, so this is the effective vanishing theorem. So one of the things that you see in Serre's theory of cohomology for coherent sheaves is that if you twist, okay, if you tensor by some ON for n big enough, all the higher cohomology, H1, H2, and so forth, will always vanish. Okay, so this is part of Serre's theorem. But you don't know how big you need to take n to be. So it's good for theory, but if you want to actually use it in practice, it's hard to use in practice, okay, for specific examples. Here, you've got an actual specific bound for when you can guarantee this is equal to 0. Okay, once this degree of D, that degree is big enough, and that's determined by the degree of this omega X. Once it's at least this big, or bigger than this rather, then you'll have H1 equals to 0. Okay, we'll see in a different video how this can be used. But let's go ahead and prove this very effective vanishing result. So what's the H1 O of D? So let's just use the formula here. This is isomorphic to the vector space dual of the HOM. So you HOM that OD into omega X star. Again, remember, if you tensor by an invertible sheaf, that's a category equivalence, so we can do that to change this HOM. Okay, tensor by O minus D to make this OD to an O, and this omega X goes to omega X minus D. So that's what you have here. And of course, HOMs from O into something is just H0, so that's H0 of omega X minus D, the vector space dual. Okay, so that's the first part that we have here. And the second part is to check that this actually vanishes. Okay, and the key point is that we actually have vanishing theorems for H0. And we're going to use, to get the vanishing theorem from H1, we're going to use the vanishing theorem for H0. So what's that? Or vanishing result there. Okay, so suppose you have degree of D is bigger than the degree of omega X. What's the degree of this thing here, omega X minus D? So that's the tensor product of these two. And remember, the degree is additive. Okay, it's a multiplicative. It's a group homomorphism. So it's the degree of omega X plus the degree of O minus D, which just means you subtract the degree of D. And by assumption, this degree is bigger than that, so this is negative. So we have an invertible sheaf with a negative degree. And of course, this H0 of this invertible sheaf, they correspond, okay, the elements inside here, or the one-dimensional subspaces inside here, correspond to effective divisors, okay, which are linearly equivalent to the divisor that gives this. Okay, so they're the ones which are isomorphic to that. Okay, So O of those divisors are isomorphic to this invertible sheaf here. Okay, and of course this is zeros because the degree is 0. Okay, degree is negative rather. Okay, so that degree can't be negative. Okay, and that completes this corollary. So if you're wondering, well, what is this degree of omega x? Well, so that's something that actually we can state more precisely in terms of this genus, which is the more usual sort of invariant to look at. Okay, so so we'll see in the next video on the Riemann-Roch theorem for curves that the degree of omega x is actually equal to twice the genus minus 2. So we do have a fairly effective way of looking at that. So for example, if you want to do this in the case of the projective line, okay, the genus there, if you look at h1 of the projective line, h1 of O we know is 0. Okay, so that's 0. So here we've got minus 2, and omega x is O minus 2, and the degree of that is minus 2. So we see that this formula is verified in the case of P1. And so that gives you that, if you put this together with this here, that tells you that as long as the degree of D is bigger than 2G minus 2, okay, twice the genus minus 2, okay, once you have that degree, then H1 of this OD vanishes. I hope you enjoyed this adventure in pure mathematics.